Okay, good evening. Welcome to the week 5 tutorial for the NPTEL course Solid Mechanics. I am Anay and I'll be conducting these sessions for this course. In this last week, Professor Ajit taught the concepts of longitudinal strain. How do we calculate it? Shear strain. Again, how do we calculate it and what important assumptions are there? What is its geometric interpretation? The concept of local volumetric strain, strain tensor, local rotation tensor, and finally the similarity between stress and strain tensors. So, okay, we'll so the first problem asks the diagonal elements of a strain matrix. Strain matrix are okay. So this is our strain tensor. So, and as we know, it is given by half of grad u plus grad u transpose. The annotations are visible, right? Okay. So the first question asks, what do the diagonal elements of the strain matrix represent? So if we write, yes. So if we write it in, they are longitudinal strains. So if we write it in matrix form, what we see is dou u1 by dou x1 half of dou u1 by dou x2 plus dou u2 by dou x1, again half of dou u1 by dou x3 plus dou u3 by dou x1 and half of dou u2 by dou x1 plus dou u1 by dou x2, dou u2 by dou x2, half of dou u2 by dou x3 plus dou u3 by dou x2, dou u3 by dou x3, half of dou u3 by dou x1 plus dou u1 by dou x3, half of dou u3 by dou x2 plus dou u2 by dou x3. So as someone pointed out, these diagonal elements are essentially of the form dou ui by dou xi, which is nothing but the longitudinal strain along the coordinate axis ei, where I will be 1, 2 or 3. Similarly, the off diagonal elements will represent half of the shear strain values. So when I is not equal to j, then the off diagonal terms are dou ui by dou xj plus dou uj by dou xi, which is nothing but half of the shear strain with directions along coordinate axis ei and ej. This is clear, right? Very straightforward question based on definition. The second problem asks, suppose there are two perpendicular line elements at a point. So this is our body and these are our two line elements n and m, perpendicular to each other. After deformation, the angle between these 2 points changes to 85 degrees. So maybe some force like this is applied. There is some fixed boundary condition, and we end up with, so this as the deformed configuration. Then this point x, capital X, gets mapped to small x, and the line segments are now n hat and m hat. The angle between these two is told to be 85 degrees. So the amount of shear strain developed here would be 5 degrees. Yes. So shear strain would refer to shear strain between two perpendicular axes, two perpendicular directions n and m. So n is perpendicular to m. Would be change in angle between n and m. Does anyone remember the formula for calculating shear strain? Shear strain at a,
times of strain tensor matrix n dot m.
yes, twice of strain tensor matrix. Okay. Okay, so the third question asks to find the axial vector for the given skew symmetric matrix. So this is a skew symmetric matrix. What is the definition of a skew symmetric matrix?
A transpose equals to minus a.
Exactly. So if we have like a matrix A, it is skew symmetric if A transpose is equal to minus A. So from this we can see that the diagonal elements will be 0, which is obviously the case here. And we are asked to write this in a actual vector form. So do you guys know how to do that?
Yes, sir. 8 minus 6 minus 2.
And where does this definition come from? Do you remember that? It comes from cross product. So suppose you are taking the cross product A cross B, then this is same as writing skew symmetric second order tensor skew symmetric matrix corresponding to the vector A, which will be a second order tensor, into the vector B. And from here, like if you remember the definition of cross product, you typically have P1, P2, P3. And if we want to say write it down in component form, then this is nothing but A2 B3 minus A3 B2, then A3 B1 minus A1 B3, and A1 B2 minus A2 B1. If you see this is nothing but same as, so you can see that this corresponds to this matrix. So minus 8 is nothing but minus A1, so A1 should be 8, A2 should be minus 6, and minus A3 is 25, so A3 should be minus 25. So your A matrix is nothing but 8 minus 6 minus 25. This is the this is what you said as well, right? 8 minus 6 minus 25.
Yes, yes, sir.
Yeah, good. Okay, the fourth problem asks which of the following statements hold true for the given strain matrix. So we are given a strain matrix 7, 5, 0, 5, 10, 0, and 0, 0, 0. Uh, okay, so the first option is regarding volumetric strain. So the local volumetric strain, do you remember what it is?
Trace of strain tensor matrix.
Correct. Trace of the strain tensor matrix, which is nothing but 7 plus 10 plus 0, which is 17. So the first option is correct. The second and third options are concerning the shear strain gamma xy. So how do we calculate gamma xy from strain matrix?
Gamma xy by 2 equals to epsilon xy.
Exactly. So gamma xy by 2 is equal to epsilon xy, which here is the value 5. So therefore your gamma xy should be 10. So this is wrong. This one is right. And finally, it asks about shear strain gamma xz. Again, gamma xz by 2 is epsilon xz, which should be which value? This value, right? So gamma xz turns out to be 0. And what is epsilon zz?
0.
Okay, so in this matrix you can see that epsilon xz is 0, epsilon yz is also 0, and epsilon zz is also 0. So what does this tell you? Is this some special form of strain?
Planar strain dimension.
Exactly. So this is a plane strain condition, which means that the displacements and strains are constrained to be in only two dimensions. Here it would be like epsilon xy is a function of, sorry, epsilon xx, sorry, ux should be a function of xy, uy should also be a function of xy. Okay. The fifth problem, it's a true or false statement. The deformation gradient tensor, so deformation gradient tensor F, can be expressed as a sum of identity tensor, a symmetric tensor, and a skew symmetric tensor, where the symmetric tensor refers to rigid rotation. So if you remember the definition of deformation gradient tensor, F is I plus grad u, right? And we can split it as I plus half of grad u minus grad u transpose, half of grad u plus grad u transpose, plus half of grad u minus grad u transpose. So this is your identity tensor, this is your symmetric tensor, and this is your skew symmetric tensor. So if you remember this, as we also discussed in the first problem, this refers to the strain tensor, whereas this represents rigid rotation. The given statement says that the symmetric tensor is the strain tensor. Is the sorry, the symmetric tensor is the rigid rotation, which is obviously not true, right? The symmetric tensor is the strain. Symmetric tensor represents strain, whereas the skew symmetric tensor represents rigid rotation. So this statement is false. Okay. Okay. Problem number 6. Which of the following special cases do 5 of the strain compatible in which of the following special cases do 5 of the strain compatibility conditions get satisfied trivially? So do you remember the strain compatibility conditions? What do they physically represent? Can anyone say?
Sir, can you please explain that one? I didn't understand.
Okay, strain compatibility condition. Okay. So we start off with, say, the strain tensor, and we know that this is a 3 cross 3 symmetric matrix, right? Which means that it should have a total of 6 independent components, 3 diagonal ones and 3 off diagonal ones. Now, what you could do in theory is take some 6 independent functions corresponding to epsilon xx, epsilon yy, epsilon zz, epsilon xz, epsilon yz, and epsilon xz. Sorry, epsilon yz. You could, in theory, take 6 independent functions, but what we see that these are actually coming only from 3 displacement components, 3 independent displacement components: ux, uy, and uz. So, like, while the matrix form may suggest that we have 6 independent components, that is not the case, because, say, if you want to write epsilon xx, it will be dou ux by dou x, whereas epsilon xz would be half of dou ux by dou z plus dou uz by dou x. Clearly, if you want to find epsilon xx, sorry, if you want to find ux between 2 points, if you want to find ux between 2 points, what you could do is integrate epsilon xx dx. Suppose this is x1 and x2, going from points x1 and x2. So this is what we are saying is one estimate of ux. But another thing you could do is take like a curved path between x1 and x2. So here, or say, like, go from, say, going at 45 degrees, something like that. All of these different paths, if you have, like, say, 6 independent functions, could end up giving you different values for ux, which is obviously not true, because these are 2 points whose displacements we are looking for. All these integrals should be path independent. As an example, I'll use the simple case of epsilon xx, epsilon yy, and gamma xy. We know that gamma xy is dou ux by dou y plus dou uy by dou x. Similarly, epsilon xx is dou ux by dou x, and epsilon yy is dou uy by dou y. if I do a double differentiation of epsilon xx with respect to y, I'll end up with dou square epsilon xx by dou y square is equal to dou cube ux by dou y square dou x. Similarly, dou square epsilon yy by dou x square if I do, I'll end up with dou cube uy by dou x square dou y. And if I take a derivative of gamma xy with respect to dou y dou x dou y, I would get dou square gamma xy by dou x dou y. This is equal to dou cube ux by dou x dou y square plus dou cube uy upon dou y dou x square. As you can see, like if ux, since ux has independent components of x and y, these derivatives, the order of these derivatives can be interchanged, and therefore you could see that dou square epsilon xx by dou y square plus dou square epsilon yy by dou x square has to always equal to dou square gamma xy by dou x dou y. So this puts like a constraint on epsilon xx, epsilon yy and gamma xy. This is a constraint coming because we have only three independent variables ux, uy, uz, but we are looking at six components, six strain components, and as well as we need the integrals to be path independent. So by this example, you can see that how the strains are bound to be related in some way.
So, sir, from this we cannot say that those six components are independent.
Huh. So the six, you can have say like six functions for all of these six components, but they need to be such that in the end you end up with like only three independent displacement components ux, uy and uz. So they are not actually independent, even if it may seem so. The other way around to think of it is, if you say end up taking with six functions for all of these components, you need to ensure that the strain compatibility conditions are satisfied, all six of them.
Yes, sir. Sir, this is not the case with the stress tensor matrix.
No,
That
yeah, no, so that is not the case there. So there we are looking at force as well as a normal vector corresponding force as well as a cross section. Here, your strain components are necessarily dependent on your displacement. So as we derived for F is equal. So if you remember, we derived this from taking a body at x with a line segment delta x, and after deformation it goes to another point small x with line segment delta x. We use certain conditions where delta x should go to 0 and the gradients are always small. Using these conditions we derived this, and using this we derived strain tensor. Okay.
yes, sir.
Hmm. Okay, so now that that is dealt with, we'll look at the problem. So we are asked, like, in which of the cases listed below, 5 out of the 6 compatibility strain compatibility conditions are satisfied trivially. So does anyone know the answer to this? Okay, so let me write it this way. Suppose your ux is only a function of, we look at the plane. Okay, for the plane stress case, we are not even, like in our strain compatibility equations, we do not even have any uh, any equation of stress coming up directly. So that plane stress case we are not looking into. Another, the second option is the plane strain case. So ux is equal to ux of xy. Uy is also a function of only x and y, and the set displacement is 0. In this case, you get epsilon xx equal to dou ux by dou x, which is non-zero. Similarly, epsilon yy is non-zero. Gamma xy is non-zero. Epsilon zz is 0. Gamma xz is 0. And gamma yz is also 0. Right? So this is your plane strain condition. Now, as you can see, this condition satisfies this one strain compatibility equation. The other strain compatibility equations can be found out. The other strain compatibility equations can be found out by interchanging xy with say xz and yz. So if I write down the equation for yz case, I have dou square epsilon yy by dou z square. We know that epsilon yy is only a function of xy, so this component will be 0, plus dou square epsilon zz by dou y square. Epsilon zz itself is 0, so this gradient has to be 0, is equal to dou square gamma yz by dou z dou y. So this equation is also 0. Similarly, if we write down an equation in xz terms, you can again see that epsilon xx will not be a function of z, epsilon zz will be 0, and gamma xz is also 0. So in the set 1, which has 3 equations, one is satisfied and the other two are trivially satisfied. Similarly, if we look at the second set of strain compatibility equations, we have dou by dou z times dou gamma yz by dou gamma yz by dou x plus dou gamma zx by dou y minus dou gamma xy by dou z is equal to twice of dou square epsilon zz by dou x dou y. In the second set of strain compatibility equations, again we have 3 there. The left hand side contains shear strains, as we see that gamma xz and gamma yz are always 0. Gamma xz and gamma yz are always 0, whereas gamma xy is independent of z. So in all three of those equations, in all three of these set 2 equations, the LHS will always be 0. On the RHS, you will once have a gradient of epsilon zz. Since epsilon zz is 0, this will be 0. In another set of equations, you will have say dou square epsilon xx by dou y dou z. Again, epsilon xx will depend on y, but it will be independent of z. So this will also be 0. And similarly for the third case where you have epsilon yy, the gradient will be taken with respect to x and z. Again, gradient of epsilon yy with respect to z will be 0. So in all three equations, the left hand side is trivially 0 and the right hand side is also trivially 0. So all these three equations are again trivially 0. So 3 plus 2 Total we have 5 equations which are trivially 0 for the plane strain case, and the sixth one needs to be checked. Is this clear, or do you want me to try it in a different manner?
Yes.
Okay. And in the third option is when the shear strain components are 0, so you can have epsilon xx, epsilon yy, epsilon xx, epsilon yy, and epsilon zz. These are the only non-zero components, but we are not told anything about, say, their nature, what functions are they of. So we cannot say this. And again, the fourth one deals with stress. The strain compatibility equations are only on strain. So again, this one is also not relevant. Okay, let's go to the seventh problem. Which of the following interpretations for shear strain are correct? So is shear strain a change in angle between two perpendicular line elements? Is this shear strain? This going to something like this. This is perpendicular, this is not. Okay, is it that it is not the change in length of line elements, because change in length of line elements is what?
Longitudinal strain.
Yes, this is longitudinal strain. Okay, the third interpretation is is it a sliding of a set of parallel lines in a direction perpendicular to the normal? So suppose this is our normal, these are parallel lines, and they are being, sorry, this is the normal, these are the parallel lines, and they are being slid in this direction. So is this either, say, this direction or even in this direction? So is this shear strain? This is right. If you remember, if I say choose this direction, then whatever was whatever initially here is now, say, slid to a different point, which is here. So this whole plane can be thought of as shifting in a different direction. So this is also shear strain. Okay, so for problems 8 to 10, we have some problem data, and we are told that a body is deforming under the action of some load and has the following displacement components. U1 is 5x1 plus tan x3 plus 7 x1 x3. U2 is 0, and U3 is tan x1 plus 5x3 plus 14 x1 x3. So U2 is 0. What can we say about that straight away? So we see that U1 is only a function of x1 and x3. U3,
Then a plane along y-axis is equals to 0.
exactly. U3 is also a function of x1 x3, whereas U2 is 0. So this tells us that epsilon 2 2 equal to 0, gamma 1 2 equal to 0, gamma 2 3 is also 0. So this is nothing but, if you remember, this is nothing but the very definition of a plane strain condition. This this is a plane strain case. This is the plane strain condition. Okay, so let's see what are we asked to evaluate. The first one asks the longitudinal strains at origin R. So we are asked epsilon xx, epsilon yy, epsilon zz at x equal to y equal to z equal to 0. So as you observed, it's a plane strain case, right? Along x and z. Along x and z, along the xz plane. So we can say that epsilon yy will be 0, right? Always, no matter where we are, right? And what about epsilon xx? Epsilon xx is dou ux by dou x, which is dou by dou x of 5x tan z plus 7xz, right? So this is 5 plus 0 plus 7z. So 5 plus 7z. This is our epsilon xx, correct? At origin, epsilon xx at origin would therefore be 5, right?
Sir, how it will be 0? Like, as we know that it represents the displacement vector. Initially, it may be at origin and it change to some other position. So, why
Hmm.
we are taking it as a 0 contribution?
So think of
That XYZ
sorry,
is that XYZ represent a particular.
xyz will represent a coordinate system, right? So this is our body. This may be the origin of xyz or x1, x2, x3. So your doubt is that you think that this longitudinal strain should not be 0, is it?
No, sir. How that XYZ are 0?
Because we are looking at origin, right? Origin of the coordinate system. This is what we are interested in, right?
Yes, sir.
So we are asked about origin. So origin is nothing but O equal to 0, comma 0, comma 0, right?
Yes, sir. Understood.
Okay. And this is for Z, right? So for Z, we are given uz is equal to tan x plus 5z plus 14xz. Epsilon zz is nothing but dou uz by dou z. So this should be 5 plus 14x, right? And now if we want to calculate epsilon zz at origin, it would be 5 plus 14 into 0, which is also 5. Correct? Is this clear?
Yes, sir.
Okay, the ninth problem asks, it's a true or false statement. The statement is, once we find the strains from gradients of the above displacements, we need to verify if they are valid strains by using the strain compatibility condition.
Yes, there are planar strain.
Uh, okay, so here in this problem, what you have is say ux, uy, and uz as the independent components. These are displacements and these are independent of each other. And using this, we are calculating strain components to be equal to half of grad u plus grad u transpose, right? So we have like three components going into six after differentiation, correct? We don't, like, if you know the displacement, then you don't need to verify the strains using strained compatibility condition, because they will be satisfied. That is how, as you remember, we talked about, if this is a body and you have some strain and you are trying to find out displacement between 2 points, then no matter what path you take, this displacement should always come out to be equal, which means that the path, which means that the integrals of the strains should turn out to be path independent and only dependent on the endpoints. That becomes a concern, like say if we are using six components for six functions for all of these components, and then we have to ensure that they actually map back to three independent displacement components. But if we are going from say displacement to strain, we don't need to check if the strains are valid. So if you are going from displacement to strain, your strain compatibility conditions will always be satisfied. However, if you choose some strain components and are trying to find back the displacement, then your strain compatibility conditions must be satisfied. Because if you remember in the sixth problem, we started off with, we start here in this equation, right? We started off with some components ux and uy, and then we proceeded to show that dou square epsilon xx by dou y square plus dou square epsilon yy by dou x square is equal to dou square gamma xy by dou x dou y. And if we look at each of these components, like if we substitute the definition of each of these strain components, you see that this whole equation actually turns out to be an equation in ux and uy, a third order differential equation in ux and uy. So no matter what ux and uy you take, this equation will always be satisfied, correct?
Yes, sir.
Is this clear? So I mean, if you want you can check, but it's actually a waste of time, because anyways your strain compatibility conditions are derived for that purpose only, that your ux uy and uz should be the only independent components, and not these components ux ui uz should be the independent components and not your six components coming out of the strain tensor. Okay, yeah. The 10th problem: from the above displacement, the local rigid rotation at the origin will be. Okay, so this is what we have. What is the local rigid rotation? Local rigid rotation is,
Along with the strain, there will along with the shear strain, there will be some rotation, which will be same for all over the lines which is at the point, those elemental lines.
yes.
They
So
all rotate with the same angle.
same angle and about the same axis. In terms of displacement u, we can write local rotation as half of grad u minus grad u transpose, correct? And we already know a few things. We know that epsilon xx, as we calculated, sorry, this is a skew symmetric matrix, right? We need to now check what are the off diagonal components. So the off diagonal components are half of dou u dou ux by dou y minus dou u by dou x. Okay, this is getting congested. 1 second. Local rigid rotation written in matrix form would be 0 half of dou ux by dou y minus dou uy by dou x half of dou ux by dou z minus dou uz by dou x half of dou uy by dou x minus dou ux by dou y 0 half of dou uy by dou z minus dou uz by dou y half of dou uz by dou x minus dou ux by dou z half of dou uz by dou y minus dou uy by dou z 0. Since it's a skew symmetric matrix, we only need to look at the diagonal terms are 0, the off diagonal terms are negatives of each other, so we only need to say look at one side of the diagonal. So these three terms. Say. Now we know that ux is only a function of x and z, so dou ux by dou y is 0. Similarly, uy is 0, so dou uy by dou x will be 0, right? So this is 0, this is also 0, so this overall term turns out to be 0, right? Similarly, now dou ux by dou z, similarly, sorry, if you look at this term dou uy by dou z minus dou uz by dou y, this term you can also say that it is 0, right? Because uy is 0 and uz is only a function of x and y, therefore dou uz by dou y should be 0. Now we are only concerned with only non-zero term seems to be this third one, which is dou ux by dou z minus dou uz by dou x. Sorry, yeah, and half. If you remember, ux is nothing but 5x plus 10z plus 7xz. So dou ux by dou z is 10 plus 7x, right? Correct?
Yes, sir. Yes.
Similarly, uz is 10x
Minus 10.
plus 5z plus 14xz. Therefore, dou uz by dou x is 10 plus 14x, right? Therefore, your term becomes dou ux by dou z minus dou uz by dou x becomes 10 plus 7x minus of 10 plus 14x, 14z. This should be z. Sorry. So this is 7x minus 14z, right? And at the origin, you can see that dou ux by dou z minus dou uz by dou x at origin, which is nothing but 7x plus 14z at origin, is essentially 0, right? So all three terms in your local rigid rotation, all three of diagonal terms are 0, and hence your matrix is nothing but a 0 matrix at the origin. At origin, that is important, not everywhere, right? 7x plus 14z is at origin, this is 0. So w at origin. Therefore, if you want to see your rotation, magnitude of rotation theta is nothing but norm of the vector form of this matrix, which is nothing but norm of a zero vector, right? So this is 0. At origin, we can say that the rotation is 0. Is this is this okay, or do you have any doubts here?
No, sir.
Okay, and since the magnitude of rotation is 0, obviously we cannot say anything about the direction, right?
Yes, sir.
Okay, so these are all the problems that I had for this week. Do you have any doubts?
No, sir. For this week, no.
Okay. You are able to do the assignments, right, on time?
Yes, sir.
Okay, that's good. And I think till this week we are dealing separately with, till week 5 we are dealing separately with stress and then separately with strain, and now we are sort of bringing them together through some stress strain laws, so to speak. Thank you.